So good afternoon all, and this is my position is like a bit like a host as well as giving a talk as a guest. So thanks Orko for introducing the field so nicely, and that made my thing much easier. And about the BC, the very basic things already covered by in the Orko's talk. So today we will actually like to talk what we are doing at Bennett and a little bit on this quantum phase study of the different quantum phases at Bennett and our last say couple of years journey. Okay, so this is the plan of the talk. Basically we will cover two aspects, a little bit on binary BEC and a little bit on dipolar BEC. And in binary BEC we have planned to talk on the Josephson effect and a bit of Bogoliubov effect, and we will study a little bit of Roton mode and modulational instability. All these things we have planned to do while taking into account the beyond mean field interaction. For last few years, the effect of beyond mean field in Gross-Pidovsky equation is matter of intense interest. And this beyond mean field term, when we have it, from the interaction approximation, the second order term in the interaction, what happened in 2015, Petrov proposed that this beyond mean field interaction at certain region, when it can balance out all the mean field interaction, that can use as a stabilization mechanism, and it can allow some kind of liquid formation. And in 2016 and 2018, there are some seminal papers in Science and Nature which experimentally showed the existence of quantum liquid. Say this paper in 2018 in Science in binary BEC, which talked about the quantum liquid. And in dipolar BEC, there was in 2016 paper from Tillman-Fau's group where they have talked about the Rosenwig instability in quantum ferrofluid. So, and from there comes the context of supersolid. So what is this supersolid? This supersolid is nothing but a superfluid with lattice ordering. So now that sounds very strange. You have a lattice ordering and you are talking it a fluid. So a way to visualize it, a simpler way is for ferrofluid. In front of our eyes, if we have ferrofluid and if we put magnetic field under it, we can see that fluid has some nice lattice ordering, forms some lattice ordering. So that is why this they have called it quantum ferrofluid. Anyway, so going back to this, when we have this beyond mean field interaction, we have an additional contribution, and this additional contribution in 1D, the Petrov calculated it in 2016 PRL paper, and Petrov has said the additional beyond mean field contribution comes like that. And in his 2015 paper, it was in the three-dimensional calculation, and later we actually deduced this in quasi one-dimensional system. So there is a fundamental difference between a one dimension and a quasi one dimension. Quasi one dimension is more amenable for experimental realization, where actually you can have a BEC. In 1D you can't have any BEC. Anyway, so in a quasi one dimension, when we did the dimensional reduction, we found that this comes with a quartic nonlinearity, whereas in 1D, it was a quadratic nonlinearity. There is another important difference here, is that the usual mean field nonlinearity in quasi one dimension is attractive, while in 1D this is repulsive. So we actually had worked with these, and we had some solution and all these things we had. After that, recently in last year, the Nobel Prize we have seen it was given on the macroscopic quantum mechanical tunneling, and we were interested to see the Josephson effect in quasi one dimensional geometry and see what it tells us. So with that, we started. So we had a double well potential like this, where we have total effective mean effective interaction term. We have the two wells, and we later extended that also to an asymmetric double well, because what we saw, there was a spin orbit coupling supersolid paper by Ketterle's group in 2016, where they have mentioned that attaining the supersolid phase, it becomes relatively easier if you have a superlattice. And that superlattice was somewhat an asymmetric double well potential, not means it was extended asymmetric lattice. So we also wanted to see the sorry, asymmetric lattice. But in the double well potential, studying Josephson effect is a very well known problem and pretty old problem. What is new here is that studying it in quasi one dimension, which we were interested. In 2024, the 1D in 1D with beyond mean field interaction results came up. We started from there and we did the two mode method, and we systematically tried to separate it out, the 1D case and the quasi 1D case, because people get a bit confused about the difference between them and how the maths change because of that. So we did this calculation, and here this is my effective term in 1D case and quasi 1D case, and this is in my 1D case. This additional term is the phenomenological three body interaction. We wanted to see, let's skip that and see if there is any effect or not, because recently in one of our study, what happened in Physics Today, there was a Barboot's article while covering this quantum liquid story. And there, very interestingly, there was a rebuttal letter in Physics Today by Alan Bulgak. Bulgak, it's by Bulgak, that pointing out that I have already said the existence of quantum liquid in 2003 PRL paper. There he talked about, it's a theoretical paper where he proposed it, and that was using a three body interaction. So his argument was that why my work has never been cited properly in your idea of quantum liquid. So from there, actually, we got the idea, let's see what plays a major role in the beyond mean field interaction, because both are apparently pretty weak, beyond mean field or three body. And with that, in 2024, we have a paper on studying the through surface tension in 1D and quasi 1D, where we had this three body term. So here also we continued with that and we did our calculation. Here we have the Z parameter and we have the theta parameter. And if we do the maths for 1D and quasi 1D, you can see the differences here as it is coming. This gamma here, this is for quasi 1D and this is for 1D. Well, in 1D, then we solve it numerically and we can see a transition which has already been observed. There is nothing new, much new here. Transition from a Josephson state to a self-trapping state, and this lambda parameter, critical lambda parameter we have for beyond which we can see self-trapping and below which we can see Josephson oscillation. Now what happened, there is a thing which was initially we also overlooked. All studies of Josephson effect in Ross-Pitavsky equation, they actually talk about the mean field interaction which is repulsive. Now here, when we go to quasi 1D system, my mean field equation is actually attractive and beyond mean field is my repulsive. So there is a fundamental change, and in quasi 1D, then we did the calculation and we were able to see the Josephson side as well as self-trapping side. But the conditions for self-trapping and Josephson oscillation actually gets swapped. And here this lambda parameter, this critical value of lambda parameter with different interactions, if we have only mean field, attractive mean field, if we are having the attractive mean field and a repulsive beyond mean field, so where the movement of this critical lambda parameter is summarized here. So if we now study this Josephson frequency as a particle number, we actually observe in that case the three body actually makes its contribution. For large particle number, this my Josephson frequency gets a bit straightened due to three body interaction, while in absence of three body it has a somewhat like a non-monotonic curve which gradually comes to 0. And we study the phase and Z together, and we summarize it. There's a 1D case, quasi 1D case and asymmetric quasi 1D case. And what we see, what is the main conclusion from here, is that in asymmetric double well is actually more favorable to actually experimentally observe this Josephson oscillation, and so that will allow you to experimentally verify the effect of all the interaction playing. So then we extended this supporting study as a Bogoliubov excitation, and in both the cases we did the Bogoliubov calculation, and there interestingly we can observe some Roton-like minima for both 1D and quasi 1D for certain critical momenta and some very low density limit. So this is going in under review now. Now then we move to the dipolar BEC, and this is again I have this mean field interaction, this is my beyond mean field interaction, dipolar and three body, and these are all the details of the parameters, and these parameter values were chosen from following these articles. Here what we see when we solve this equation numerically, initially starting with a Gaussian ansatz, we see slowly a fragmentation of the localized solution. This localized solution, as we increase the dipolar interaction, we can see a gradual fragmentation of this. So here it is with a 5 GDD, this blue line, while you see this red 22 GDD, there is a kind of fragmentation. Now another way, now keep the dipolar interaction fixed, we now play with the mean field interaction, and there we get this flat top droplet solution, and there also we observe a fragmentation for relatively high mean field interaction. Now the point is, so both cases we are seeing the fragmentation, but what exactly involved in it? So we need to do something more to understand this fragmentation. So here these are the parameter values which is being used. So for that we actually used we wanted to calculate the superfluid fraction as well as the condensate fraction, and of course the dispersion. So we did the dispersion calculation, and very interestingly here we see clear Roton like mode, and You can see relatively lower dipolar interaction strength. The roton softening is there, and but if we gradually increase, so somewhat here, we start getting some unstable region here, and this at red, this value 21.79558 GDD, we get a actual roton minima. So doing systematic study, we get this. So this roton minima kind of a signature for the existence of the super solid phase. Now when we study the superfluid fraction and condensate fraction, this axis is superfluid fraction, this axis is the condensate fraction. We see very interestingly, superfluid fraction gradually comes down as we increase the dipolar interaction. That is quite natural. As more crystallization is happening and the supersolid phase is emerging, my superfluid fraction gets suppressed, while that condensate fraction remains more or less similar. However, what happens for the flat top case? When you look at the flat top case, we were getting the real lines here, and then we are wondering what is happening. Then when we try to look at the complex part of the dispersion relation, we got very nice modulation instability related side lobe generation, and these side lobes, the area of the side lobes are gradually increasing as we are getting the fragmentation part gets more and more starts dominate. However, the superfluid fraction in this case remains more or less unchanged. So here what simply we can say, there is no from this droplets fragmentation, the droplets are getting fragmented, but they are not actually creating any supersolid. But these localized structures, when they get fragmented, it gives a clear signature that these fragments are started forming the supersolids. So this is the similar thing we did with the varying particle number, and we see again the side lobes of the modulation instability. So this is the total, you can say, the takeaway. So from the elementary excitations, this Josephson effect and Bogoliubov theory, we have talked about the Josephson oscillation to self-trapping phase change and their phase boundaries we discussed. And in the dipolar BEC, we studied through dispersion relation, superfluid fraction, condensate fraction calculation. So the possible reasons of these fragmented states and what are these fragmented states, that's what we tried to calculate. So this is what in a nutshell what we wanted to say. So here my PhD student Shivam is here, so most of the work is by him, and apart from that there were one NRF project associate Ibrar and CSIR JRF Suhail Rashid who have contributed in this work. Also, I like to thank ANRF and CSIR for the funding, and with this I like to thank you.
Thank you all for the talk. So there must be some questions. Yeah. Please.
Thank you, sir, for the talk. So I have a question that what is the reason in the condition of swapping, the self-wrapping and the Josephson oscillation condition?
Yeah. So what's happening when you are having the interaction, the mean field interaction is now negative. So in the negative side, it's this Josephson oscillation and the self-trapping what we are measuring, that's in the negative side. So that's, and it was in the positive side. So that's why it is actually the greater or less the sign it changed.
Okay, and I have another question. What is why the superlattices have the double well potential?
Yeah, super lattice not directly, I cannot say it's a double well potential, but if you go back to that paper, you will see this super lattice is some kind of a combination of, because these lattices are created through some optics, bichromatic lattice. So these bichromatic, say if you tune the frequencies, so these the lattice, it's not the optical lattice, is not an uniform optical lattice. There is some unevenness, and that if you just look at snapshot, you can actually mimic it through like a asymmetric double well. So that was the motivation to use the double well here.
Questions? So asking question to Bennett University always favor. Maybe it will be covered tomorrow in Times Media. Yeah, so we'll move on to the next
Okay,
talk.
thank you.
The student contribution. Again, thank you, Ayan.
Thank you.